Chemical bonding, guys, is Unit 4 that we're going to start. We have alluded to it a lot over the last unit because we were dealing with electron configurations. And what's that magic number that they're all trying to get to? 8. Okay, 8 what? Valence electrons. Now we're going to talk about the specifics of how they get to 8 valence electrons. So, we're going to talk about the first few types of bonds kind of today. That's the goal, is to kind of have an overview of the 3 major types. Kind of get that terminology down, start talking about what's going on, start drawing some structures of how to draw the bonds. And then over the next few days, guys, we're talking about things like polarity. We're going to talk about intermolecular forces in this unit. And then we're also going to discuss shapes of molecules. Okay, so we're going to start dealing with how things are put together. That's going to lead us right into Unit 5, which is naming compounds. So you'll see a lot of formulas in this unit, and then next unit you'll learn how to name those compounds, those formulas. All right, one thing I've started to add in my notes is hopefully what page you should be on in your note packets. I will try to start doing that more so you won't be as confused. Again, if I'm ever going too fast or you're confused, ask me. Okay? So what's a bond? All right? It's a force, guys, that holds one atom to another in a compound. Super simple. All right, this is just kind of the general overview of what's happening. To break a bond, this is something you probably want to add to your notes right here, this one. It requires energy to be put in to overcome the forces of attraction. So if you are putting energy into the system, what type of change do you think that is? Bond breaking is what then? If you're putting energy into something, it's either endo or exo. If you're putting energy in, we've talked about endo. Yeah, it's endothermic.
Where is this?
This is, you're adding it, right? So like it says up here at the top, you're adding this to page 2. You add it to the top or off to the side. If you want a separate note sheet, guys, you can staple to it. All right, I'm giving you the big ideas, but there's a few things that we're going to add to that. Okay? So to break a bond, guys, requires energy. All right, that means it's endothermic to break the bond. It takes energy together. So if you make a bond, you take 2 elements, you make a bond, they come together, you release energy. So what would that be? Yeah, bond making is exothermic. Really, guys, the big thing, if you just put exothermic and endothermic, that's the big idea you need to add. All right, you don't have to add every single word up here. All right, bond breaking is endothermic, bond making is exothermic. Okay, so we're going to talk a little bit about energy here in this, in terms of that, but we will come back, guys, and hit on this again when we get into what's called kinetic molecular theory, KMT, toward the end of January, early February. Okay? So we'll talk all about the energy that's associated with things. It all comes back together. That's the beauty of chemistry, is where we talk or introduce one thing, but we come back to it and hit it again later on in the year. All the stuff we've done up to this point, we will come back and keep doing all throughout the year. The basics really drive a lot of those concepts and those big ideas that we talk about later on in the year. All right? So, breaking is endothermic, bond making is exothermic. All right? Compounds, guys, then have less energy, which means they are more stable than just the single substances that they form from. Okay? They're more stable when they have bonds together because it's less energy. Think about it. Why might that be true? What are they all trying to get to? 8 what? Valence electrons. So when you have an element, guys, that's by itself, and it has 1, 2, 3, 4, 5, 6, or 7 valence electrons, there's kind of this want and desire to get to that magic number of 8, being stable. They want that outer energy level filled. Okay, so they will do different things. Some will lose electrons, give them away. Some will take them in. Some will share, kind of enter into a mutual agreement to share electrons to form a bond, because, again, it all comes back to energy. Electrons, we've said, are what? Atoms are, just like we are lazy. They want to be in the lowest energy state possible. And that's what's driving a lot of stuff in chemistry. So, for example, guys, you don't have to write this down. Water has less energy than the hydrogen and oxygen from which it's formed. Okay? This is a piece you do want to have in your notes. Energy stored in a bond is known as potential. All right? It's the potential, not a potential energy. It's the ability to undergo a change, which would be something like it has the potential to break that bond or to release that energy. Okay? All right, so the octet rule, this is one of your vocab terms. Atoms are happy with a full valence shell, which is 8 electrons. Gain or lose those electrons or share. So they have 3 different options. They can gain electrons, they can lose electrons, or they can share. You don't have to jot this all down. We're going to get into this here in a minute when we start talking about the types of bonds. So there are 3 types. These are the 2 that we're going to talk about mostly in this unit. Metallic we're going to introduce, but we're not going to really do too much with it. There's going to be a couple big key ideas that you want to make sure you know about metallic bonds. But ionic and covalent, that's where the money is. Okay, that's where we're going to spend the bulk of our time in this unit. And then specifically, covalent, the latter half of this unit, when we get into next week, when we start talking about valence shell electron pair repulsion theory, is all dealing with covalent compounds. All right? So, we're going to kind of jump around from the order that's in your note page. Page 3 is where you want to be, guys. We're going to talk about metallic first, kind of define it and what's going on, the key idea that you want to remember with metallic bonding, and then we're going to move on to the other ones we're going to spend the bulk of our time with. So, it's bonds between atoms in a metal. Guys, it can be 2 different metals, like steel, where it's... Oh, boy. I always forget that. No, steel's a bad example. But we have 2 metals together, and they come together to form like, a mixture of metals. Or just a single one, like if you had a gold bar. The atoms in that gold bar have metallic bonds within other atoms of gold. Okay? They have a crystalline lattice, guys. Here's the key thing. sea of mobile electrons. Make sure you highlight or underline that in your notes on metallic bonding. All right? The phrase you're going to hear is mobile electrons. I'm sorry, wrong thing. Atoms in a sea of mobile electrons. Okay, that's the key idea there. What that means is they are freely moving electrons. What do you guys know about metals in general? They're good what? Conductors, right? That's, when we talk about plugging something into an outlet, what's in that wire? It's a piece of metal, probably copper. Okay? It allows those electrons to move. That's all electricity is moving, flowing electrons. Okay? Any substance that has moving charged particles, mobile electrons or ions, will conduct electricity. Ions are going to be a big thing that we will talk about a little bit in this unit, but later on as well. They have a high melting point and boiling point because their bonds are strong. So we will talk about bond strength and kind of compare the 3 different types. You want to add these properties in there that you probably have heard about and thought about with metals before. They're good conductors. They've got high melting and boiling points. Think about it. If you put a piece of aluminum or cast iron pan on a stove or on a fire, does it melt right away? Aluminum can. Be careful with aluminum how good quality it is. But iron's not going to melt right away. It takes a lot of energy to get metals to melt. Okay, so we have high melting and boiling points. Malleable. What does that mean? You can bend it, all right? It's bendable. All right? Here's the idea. Positive ions in a sea of mobile electrons is the idea that you want to keep in mind. The phrase sea of mobile electrons. They can move freely. That's what makes them such good conductors of heat and electricity. So here's kind of a diagram. You don't have this in your notes, but basically, guys, what this is showing is you've got fixed atoms, all right? And then the black dots are your mobile electrons. They can move all around. So this diagram over here on the right, I'm going to show you a visual here in a minute or two of all the different types of atoms and kind of, what to think about. But these electrons here, you've got those positive centers, those nuclei, right here with those mobile electrons being able to move freely. All right, so our second type of bonding. Again, we kind of go through metallic very quickly. That's all we need to know are those few properties, sea of mobile electrons. That's the big idea you want to remember. Ionic. We will talk a lot and deal with ionic bonds a lot. Okay? What does the word ionic mean? Well, it comes from the word ion. What does ion mean or refer to?
Charged particle.
Charged particle. Why? What forms an ion?
When the electron gets added to an atom or removed from an atom.
Absolutely, guys. Ions are formed when atoms gain or lose electrons. When they gain or lose electrons. So make sure you have that down around ionic bonding. There's something that's changed in those electrons. Okay? You've gained or lost those. And that's going to lead us into what's happening within and forming ionic bonds. If you have an ion, you have a what with it? How do you know you have an ion?
Charge.
you have a charge, okay? So keep that in mind as we go through this. What holds ionic bonds together are those charges. We've talked about charges a little bit. Like charges on electrons want to do what? Repel each other. But if you have opposites, opposite charges will do what? Attract. And that's exactly what makes an ionic bond. You've got positive ions. What are positive ions called? Cations. Terms you need to know by now. Negative ions are called anions. Okay? So those positive and negative pieces that form from the gaining or losing of electrons, let's quick review here. Cations do what with their electrons to form that positive charge? They will lose the electrons, and anions then will gain electrons. So when you had that transfer, and that's going to be the key word here with ionic bonds, when you've had that transfer of electrons, you get those charges. It's those charges, folks, that hold the bonds together. The opposites attracting. And not only do they hold them together very, very, very strongly. Think about it like two strong magnets. All right? It takes a lot to separate those magnets. Same idea here with the bonds. All right? Jot this down. One easy way to identify if you have an ionic bond or not is going to be this right here. Ionic bonds, guys, are made between metals and nonmetals for the most part. Okay? Metals and nonmetals. What's that? Like sodium chloride, right? Sodium is a metal. Chlorine or chlorine is a nonmetal. That's exactly what we have going on here. The other key is that it's formed when they are transferred. This is a key term. Jot it down, star it, underline it, highlight it in your notes under ionic. There's a transfer of electrons. That's a big difference from what's going on with covalent bonds. This is what separates covalent from ionic. Now, even though I say metal and nonmetal, we're going to learn in our next unit, guys, there's these things called polyatomic ions. Okay? So I'm going to jot that down. Okay? So you can either be between a metal and a nonmetal or a polyatomic ion with a nonmetal. What do you think that term polyatomic ion means? First off, it's an ion, so it has a what? It has a charge. Okay? Yeah, exactly, guys. In a polyatomic ion, there's more than one atom. Why do you know? Why do you say more than one? Poly. Exactly, guys. That prefix poly means more than one. You're going to have a whole list of polyatomic ions that you're going to have to memorize. That's coming in Unit 5, okay, in a couple weeks. So for right now, hold on to that little piece, and we will talk more specifically in Unit 5 about those polyatomic ions. But it just means you have multiple atoms making up a single ion, meaning one single charge with it. All right. So this diagram right here that you don't have in your notes, it's showing a transfer. So sodium, guys, how many valence electrons does sodium have? Have your periodic tables out. You're going to want them. It's got one. How do you know it has one valence electron? Because what group's it in? It's in group 1. Is it easier to lose 1 or gain 7 to get to 8? Lose 1. Sodium, guys, is very willing to give up that 1 electron. Now let's take a look at chlorine. How many valence electrons does chlorine have? It's got 7 because it's in group what? 17. All right, it's in group 17. So, is it easier to lose 7 or gain 1? It's going to gain 1. Bless you. So, guys, you have a perfect match here with sodium and chlorine. One wants to lose an electron, give it away. The other one wants to take that 1 electron in and hold on to it. So they will very readily form their ions. Okay, Na plus and Cl minus, and then this is what your bond would look like right here. Okay, you've got that positive in the sodium, and you've got that negative in the chlorine. Those opposite charges pull them together to form a bond. Okay, that's what keeps those together. We will draw pictures here in a minute to kind of show this whole process as to how you're going to draw the bonds. All right, but this is what's taking place. It's those opposite charges within it. Okay, metals tend to lose electrons. Where are the metals located in your periodic or on your periodic table? What side of the periodic table? Yeah, they're to the left. Doesn't mean they can't gain electrons. 99.9% of the time, they're going to lose those electrons. Nonmetals, guys, will tend to gain electrons. All right? Where are nonmetals located?
To the right of the stairwell.
To the right. Now, we've talked already, guys, about this stuff. All right? Hopefully you notice this with your lab when you graph periodic trends. Which ones have low ionization energies? The metals do. Okay, you can go back and look at your graphs. Nonmetals, they're the ones that have high electronegativities. They want to gain those electrons. We looked at those trends. Now, doesn't mean they're always going to do that. Sometimes they will lose depending on what they're bonding to. We'll talk more about that when we do oxidation chemistry later on in the year. Okay, but it's that exchanging of electrons that forms a bond. Okay, so again, a lot of these pieces that we're talking about today hopefully are somewhat review for us. All right, which is why I'm going a little bit quicker. This is what a an ionic bond might look like. It's got a very, very neat and organized structure to it. You can see you're alternating between sodium ions, the yellow ones, and then chloride ions, which are the green ones. This is what we call a crystal lattice structure. Very, very, very neat and organized. When you take a look at crystals of different ionic compounds, when they break apart, they break in very rigid, jagged, straight-line edges. Okay, I will show you guys some pictures of these a little bit later on or tomorrow in lab. We'll get a chance to look and see what they look like. But they form very, very nice crystals. Anytime you've seen crystals, like if you've ever seen salt, we'll dissolve some salt and we will form some crystals. We'll do that tomorrow in lab. And you can see that it's very neat and rigid and organized. Covalent compounds we're going to learn are not as neat and organized. The name's bond, ionic bond, shaken. Oh, I'm sorry, I even messed it up. Man, I can't upload this video. I've just completely messed it up. Taken, not shared. Huh? Okay, rough crowd today. Ionic bonds, guys. Difference in electronegativity. We'll come back and talk about that tomorrow. I want to get through covalent bonds. So here's an example of how sodium reacts with chlorine. Okay, we're going to start by writing out or drawing our electron dot diagrams. Okay, what do our electron dot diagrams show us? Valence electrons. Okay, so when we do ionic bonding, we will draw an arrow between the two showing that, hey, this lone electron guy right here that our metal had is going to go over. It's going to transfer to another substance. We're going to do a couple examples here right now. So let's start off with magnesium and sulfur. All right, this is on page 2 there in your notes, about halfway down. First thing we got to do is write our Lewis dot diagrams. How many valence electrons does magnesium have?
2.
Okay, it's got 2. Sulfur has how many? 6. So when we start to write a reaction out of where two pieces are, two different elements are going together, we put a plus sign between them. Okay, we put a plus sign. We'll get into more specifics again later on in the year when we do our unit on reactions. But for now, we're adding two things together, put a plus sign between them. Then we're going to draw an arrow. Whenever we see an arrow, guys, that's saying, hey, a reaction has taken place. Something new is going to be formed. What we're going to do here with ionic bonds, how do I know that this is an ionic bond, besides it saying ionic bonds up here at the top? Okay, magnesium is going to lose its valence electrons, give them to sulfur. It's a metal and a nonmetal, guys. That's the easiest way to understand. We're going to also look at the difference in electronegativity values tomorrow, but to keep it simple, metal and nonmetal. So, magnesium's got 2. It's going to lose those 2. It's to the left-hand side. It's got low ionization energy. Means it readily gives up its electrons. Sulfur needs how many? It needs 2. Oh my goodness, it's a perfect match. We're going to draw arrows showing kind of where they're going to pair up with. Those ones that are alone all by themselves. Notice we're drawing arrows. Ionic bonds, guys, we use arrows to draw those in because it's signifying that we have a transfer. One is giving, the other one is taking. There's a give and take happening. When elements give away or take in electrons, what do they now have with them? When they gain or lose, they have a charge, okay? So when we write our new structure, guys, on the right-hand side of our arrow, we're going to have charges. And there's a special way that we've got to write those in. We're going to start off by writing our element. But we're going to put brackets around them. Anytime they have ions, guys, we have to have brackets or parentheses around them. Magnesium had 2 valence electrons to begin with. Now it has how many? It's lost 2, so what's the charge going to be?
Positive.
Yeah, positive 2. So 2 plus or plus 2, either or. And then sulfur, what's its charge going to be? Yeah, it's going to be minus 2 because it gained those 2 electrons that magnesium gave away. Now, sulfur is also going to have something else with it. What do you think that might be? It's going to be different than magnesium. What do you think sulfur is going to have?
Is sulfur going to have the dot diagram?
Yeah, sulfur, guys, is going to have not only the dot diagram, but it's going to have how many dots now?
8.
It's going to have 8. Why? Because it took in those other 2. Now, for the first few examples, I'm going to use X's to represent the ones that it brought in. You don't have to use those. It's just to show you guys, hey, these other 2 here that are the X's, where'd they come from? They came from magnesium. This is how we draw structures for ionic compounds, guys. Kind of the way I think about it is, hey, they have very crystalline structures. So when we draw the brackets, it kind of makes boxes to make them in order, kind of very structured and organized. Maybe that's some way to help you remember that they have a very crystalline structure when they form their bonds. All right? But the big thing, what do they have to have? Ionic compounds have to have what in their final diagram? What did we just draw in? Charges, right? Ionic, guys. Ions have charges because they gained or lost electrons. So, example number 2, calcium and iodine. Calcium has how many valence electrons?
2.
It's got 2. Iodine has how many?
7.
Okay, so they're going to go together. Who's going to lose electrons? Calcium. Who's going to gain them? Iodine. How many is iodine going to gain? Oh, it's only going to gain 1. Okay, so iodine's happy with 8. Is calcium happy now, folks? Why not? Because how many does it still have? It still has 1. So what's going to have to come into play, Alex? Yeah, another iodine, guys. So when they give you only 2 elements, you can use more than 1 atom to get rid of those valence electrons. And that's exactly what will happen. Calcium now, all right, is going to give its other electron to another atom of iodine. So now our final structure here over to the right, calcium, is it going to have any dots around it? Why not? Because it gave those electrons away. What will it have on the outside of the parenthesis? It's going to have a plus 2, right, for its charge. And then how many iodines will we have to draw? 2. And they will all have 8 dots around them. What's the charge on iodine going to be? Right. Do I have to put a 1 there, do you think, with that minus? No. Guys, if you have just a single plus or a single minus, it's assumed to be a 1. So we've got 2 iodines here. Okay. Now, with that, okay, we got to write a formula. What's our formula going to be for our new compound in example number 1? What do you think it's going to be? First one.
Oh, first one?
Yeah.
Oh, MGS.
MGS. You just put it together. You count up how many you have. But what about that second one? What do you think our new formula is going to be for the second one? Yeah, exactly, guys. CAI2. Whenever you have more than 1 element, it becomes a subscript. We'll get into that more in our next unit. Right now, keep it simple. It is that way. You guys are going to do aluminum and fluorine on your own. Yeah, we're going to need 3 fluorines here because you have 3 valence electrons on that aluminum. So I've drawn 1 in there. I'm going to show all the other ones. Make sure when you're drawing structures, you've got to show every single electron. Okay, it does matter. So we're going to have aluminum. What's the charge on the aluminum going to be? Plus 3. Then we've got 3 fluorines with negative charges. Each one has how many for the negative charge? It's got 1. What's our formula going to be?
ALF3.
ALF3. ELF3. All right. So that's as far as we're going to get today.